Hello everybody. Uh, let's continue with the properties of discrete time Fourier transform today. In the last session, we have seen the two properties. That's the linearity and the time shift property. Okay. Today we shall continue with the third property, that is the frequency shift. Okay. The second property that we saw was time shift, but now the shift that we are seeing is in the frequency. Fine. So if you, this is the frequency domain, this is the time domain signal. So if you apply DTFT on the time domain signal x of n, okay, you will get the frequency domain signal, that is x e power j omega. Fine. Now see here, there is shift in this. This omega is the frequency. Fine. So this, there is a shift in the frequency, that is beta. Understand? So if there is a shift in the frequency, okay, so that shift on the time domain is compensated by giving this exponential to the time domain signal. So that is e power j beta n. Understand that? If it is minus beta, plus beta should come on the time domain. If it is plus beta, the minus beta should come on the time domain. Understand? So this is the time shift property. Let's see how they have proved this. Fine. So we're starting with the equation for the spectrum. That's the frequency domain equation. Fine. And since it is this, though the same equation can be written for the y also. Okay, that means the y of n they have taken, right? That for y of n they have taken another equation. So this x of n is substituted here if you want. Okay, so if you want to substitute this, we could have gone for substitution directly, but they have taken an extra signal y of n. That's why they have gone for this extra equation. Fine. So bring this y of n in this place. That means along with x of n and this exponential. This exponential has come in the time domain because of the shift in the frequency. Understand that? So after substituting that, okay, it looks like this. Fine. There are two exponentials now. Fine. So the two exponentials are combined. You see that? So there is e power j beta n, there is e power minus j omega n. So both the exponentials are clubbed together. Okay. So how does it look like now? How does it look like? What was now? If you compare this equation, if you compare this equation with this equation, see if there is x of, if there is omega here, it is e power j omega. If there is omega here, it's e power j omega. Understand that? So if there is e power, if there is omega minus beta, okay, so that shift is going to be there in, so it's x of, see there is a omega minus beta, right? That's why this equation is x of e power j omega minus beta. Understand? So the shift in the frequency domain is represented like this. Everybody understand that point? Okay, I explain again. See what's happening is, if there is a shift in frequency, okay, that frequency shift is reflected in the time domain by this exponential. Understand that? Okay, if it's e power minus j omega n, it is x of e power j omega. If it is omega, it's omega here. Okay, but what's happening here? In this equation, omega minus beta has come. So instead of x of e power j omega, in place of omega we write omega minus beta. So this is what is frequency shift property. Understand that? Okay. Let's move on to the next property, that's scaling. So when this case says scaling, we need to be particular about, are we scaling the amplitude or are we scaling the what is this? Are we scaling the amplitude or we are scaling the time? This is the discrete time. So P is used to scale the discrete time here. So it is time scaling, not amplitude scaling. Okay, so if you scale the time, okay, here on the frequency domain, okay, the omega is going to be divided by the same scaling factor. See this? The omega here is going to be divided by the same scaling factor. So here the time is being scaled by p. So on the frequency domain, the omega is being divided by the scaling factor p. Fine. So let's see how it goes. Again, you catch hold of the same equation. That's the equation for the spectrum. Fine. So take another equation because they have taken z this time. So in the previous problem, this was taken as y of n. Now this is taken as z of n. That's why the equation is written in terms of z here. Okay. Substitute z. What is z? Z is the time scaled discrete signal. Fine. So bring that time scale discrete signal in place of z. Fine. Next, since Pn is there, substitute that Pn as m because we're not used to see this as two variables here. So we can see x of n, we can see y of n, we can see z of n, but there should not be p into n. So we're not comfortable seeing that because we're not used to it. Fine. So what we're trying to do is we are substituting this Pn as m. So if you substitute this Pn as m, okay, there is a n here. What is this n supposed to be? This n is supposed to be m by p. Okay, so this n is written as m by p. That divided by p is given here. Now again, compare this equation with this equation. If it is omega is there, it is e power j omega. If it is omega by p, it has to be e power j omega by p, and that's what's happening here. In place of omega, we have omega p. Okay, that's why the omega would be replaced by omega by p. Understand this? So this is the time scale property of discrete time Fourier transform. Let's go on with the next property, that frequency differentiation. We have seen the differentiation in Z domain, right? It is very similar to that. It is very similar to that. So we have seen the relation between the Z transform and the discrete time Fourier transforms. If you remember that, so all these would be easier for you. Fine. So see here, the frequency domain signal is being differentiated with respect to the frequency omega. Frequency domain signal is being differentiated. Okay, that's why it's with respect to the frequency omega. Fine. So let's see the proof of this. If you do this, see, if you do this, the time domain signal is accompanied by minus jn. Okay, it was minus n x of n. Okay, dy dz, that was happening in z domain. Okay, so here it is minus j into n is there on the time domain. So let's consider the same equation. Fine. Differentiating both sides with respect to omega. So if you differentiate both sides, what happens? Now this is the equation. This is the frequency domain equation. I need this frequency domain differentiation. That's why we have considered the frequency domain equation and we are differentiating both the sides. Understand? So this would be as it is. So what changes would happen on the right hand side needs to be seen. Changing the order of differentiation. Why that's happening? Why did they take this sigma, or what is the summation out, and x of n out? Why is that? Here we are differentiating this signal with respect to omega, and the functions of omega would only be there within this differential. The rest have got nothing to do within the differential. That's why this part, the function of n, is taken out. So this exponential is also a function of n, but remember there is an omega here. So that's why this has to be differentiated with respect to omega, and the rest, which is not the function of omega, is taken out. So that is what is done here. Fine. Now, if you differentiate, what happens? Differentiating this exponential is the same exponential into minus j n. Understand that? Now, how is this done? Minus j x of n is written. This minus j is associated with x of n now. Get that point? Now, just observe this equation very carefully. Observe this equation carefully. What do we understand? Again, you have to be comparing this equation with the starting equation. Understand that? So, x of e power j omega is the DTFT of x of n. Understand? Or DTFT of x of n is this. So comparing with this equation, what is true here? So comparing with this equation, what is true? Okay, the the DTFT of this signal is this signal. See, DTFT of x of n is x of e power j omega. Similarly, DTFT of this signal is the differential of x of e power j omega with respect to omega. Okay, that's why this is true. So this is what is frequency differentiation property of DTFT is. Understand? Now let's move on to the next property, that is convolution. This convolution is there with every property, and it makes our lives easier with the transformations. Okay, in time domain, it gives us a lot of computations, but soon after you get into frequency domain, whether it is Z domain or Laplace domain or the frequency domain, okay, so everywhere it comes as the multiplication operator. Understand that? So let's take the two equations, that is for x e power j omega, then y e power j omega. The two equations are taken, okay, and the convolution of these two signals is taken as z of n. Okay, so the frequency domain of z of frequency domain signal of z of n is given by this, and we know z of n is convolution of the two time domain signals x of n, y of n. Okay, and we know the equation for this convolution operator. Okay, if the two signals are being convolved, what is that convolution given by? So that is not dealt with in detail, so that will be dealt with in second module. Okay, but here you just try remember this equation. The convolution of the two signals is given by this. Understand? Now there's a small problem here. Okay, here it should have been the time continuous time signal I've taken. Okay, this is called as convolution integral. I should have taken convolution summation, convolution sum. Okay, so it is just replace this t by n, and you just have this in this place. Okay, so this x of n convolution y of n is actually this in discrete time. Okay, so this is for continuous time. This is convolution, this is called as convolution integral, and this is called as convolution sum. So convolution sum should come here. Understand? So in this place the convolution equation for convolution sum is brought. Okay, so this is for continuous time. Okay, show the discrete time, so this has to be replaced by the summation. That's it. Understand it? So this t would become n, this t would become n. Okay, and this integral would become the summation. Understand? So after substitution of that and changing the orders accordingly, okay, the function of L is brought along with L. Okay, the function of n is brought along with n here. Understand? So this is a standard equation. Yes. Let's see. N minus L is there, right? So n minus L, let's take that as m. If you take n minus L as m, n would be m plus L. This n would be m plus L. Understand? So n minus L is taken as m, and soon after this, this becomes m. So this n would also turn as m here. Since it is L, so summation will have L ranging from minus infinity to plus infinity. Since n minus L is becoming m, so m would be running from minus infinity to plus infinity. So that needs to be changed eventually. Understand that? So this is m. If this is m, n has to be m plus L. That is what is written here. Okay. Now you have an exponential, which is the function of L. Okay, so bring that function of L here along with this summation where L is running from minus infinity to plus infinity. Okay, and now these two are in standard form. Which standard forms? We've written the equations for that. So this is x of e power j omega, and this is y of e power j omega, and these two are the products. Okay, so what is the conclusion we are drawing? What is the conclusion? The conclusion is the convolution in time domain is equivalent to multiplication in frequency domain. Understand this? So now let's move on with the last property here. That's the Parseval's theorem. So this theorem we have seen for Fourier series also. Okay, so it deals with actually the power. Okay, the power of the signal and the power density in frequency domain. Okay, so what is this? If you just see this, what is the LHS here? See, in equation 1, okay, this RJ, okay, this they are saying. Let's go on with this. So this is energy density spectrum. That means here you have energy, combined energy. Okay, here when we get into frequency domain, we come to know what is the energy at each omega. Omega is the frequency at at a particular frequency. What is the energy density? Okay, so this is energy density spectrum of the signal x of n. X of n is the discrete time signal. This is energy of the signal x of n. This is the combined energy, the total energy of x of n. What is this? This is energy density spectrum. Energy density spectrum means what? It is combined energy. Here, what is the energy at a particular frequency? So that is called as energy density spectrum. Okay, so LHS is the energy of the signal x of n, and this is energy density spectrum. So these two have to be same for any signal x of n. Understand that? So let's prove that. So let's start with the energy. That's the left hand side here. So let's consider the energy of the signal E. Fine. And see here, this is the magnitude square. So this we have seen in the first model, how when we were looking at how to calculate the energy of the signal and power of the signal, we have seen this equation. So it is magnitude square. Okay, if it is complex, it is magnitude square, or else just say x squared of n, not a problem. Okay, since we have taken the magnitude square here, okay, so this can be written as x of n into complex conjugate of x of n. Why? How can we be writing it like this? How this magnitude of x of n squared can be written as this? So yeah, what is the magnitude of this x of n? Suppose this is what the complex number. If x of n is complex number, let's say if it is a plus jb times. Say it is a plus. If it is a plus jb, I'm just talking in terms of numbers. A plus jb is not a signal, mind you. I'm just giving you an idea. Suppose this is a number a plus jb. Okay, what would the conjugate of this complex conjugate of this would be a minus jb. And if you take the magnitude of a plus jb and magnitude of a minus jb, okay, it's the same. Understand that? So the magnitude of a signal is equal to the magnitude of its complex conjugate. That's why the magnitude square can be written as like this. Okay, now see here, we know x of n can be given like this. Fine, let's see what happens next. In that x of n, okay, what is done? What is done? See here, x e power j omega is there, right? What is done in that place? Can you make out? 1 by 2 pi. So this is x of n. This is x complex conjugate of x of n. I'll tell you again. See here, if x of n is given by this, what is complex conjugate of n given by? The complex conjugate of n is given by x star n. Okay, and in this place you will have x conjugate, the capital X conjugate. So in this place, what they're going to have? They are going to have this equation, okay, wherein x e power j omega is written as x star e power j omega. So this is the equation they have written. So this energy equation is given by this. So this is x of n, which is kept as it is. Then x star of n is substituted here like this. Understand? Okay, just rearrange the summations and the integrals. Okay, so bring this there is 2 pi, right? So this 2 pi can be written as minus pi to pi, not a problem, minus pi to pi. Okay, but here you can write it as 2 pi also. So that is another way of writing this integral. Fine, so they have rearranged the integrals and the summation like this. Fine, can you see this and tell me what is this? This is x of e power j omega. Just if you take this is x of e power j omega. Now you have the conjugate and the signal. The signal in frequency domain and complex conjugate of the same signal. So if you take the magnitudes of these two, don't you think the magnitudes of these two are the same? So the magnitudes of these two are going to be same. That's why the magnitude of this and the magnitude of this multiplied would give us magnitude square. Get this point? So energy happens to be this, where this is energy density function of x of n. So this is Parseval's theorem, and this Parseval's theorem should be applicable for any signal x of n. Understand that? Okay, so this is what I had to give you today. So this is completion of all the properties. From the next session, we will have the problems. Fine, we'll be solving the problems from next session. So in this session, we shall stop it here.